Welcome back, students. In this video, we're going to look more closely at the E2 mechanism. When we look at the E2 reaction or the E2 mechanism, I want to go through a couple of things. First, we're going to start with the definition, then we're going to go to a rate equation, followed by substrate structure and regio and stereochemistry. When we're considering an E2 reaction, let's just remind ourselves what the E and the 2 mean. The E means elimination. Elimination means that we're removing a proton, so a hydrogen without its electrons, as well as a leaving group. So the E stands for elimination. The 2 stands for bimolecular. Bimolecular means that there are 2 molecules involved in the rate equation, and that's what we're going to look at next. When we consider the rate equation for an E2 reaction, because this is a concerted reaction where all the bonds are breaking and forming at the same time, or both of the mechanistic patterns of your base subtracting a proton and your leaving group leaving, that both of those are happening at once. That means that our base and also our substrate are involved in the rate equation. You need both of them. Now, some people don't call the entity that I highlighted in blue the substrate. If you go on the internet, you'll see that the majority of people, instead of calling it a substrate, will call it just like RLG for leaving group, right? The thing that has the leaving group attached. So when you're looking at the rate equation, your rate is going to be equal to the rate constant, which changes for each reaction. And then you're going to have the base in your rate equation, and you're also going to have the substrate, which again, most people will write as RLG. When we consider this rate equation, notice how it is bimolecular, bi meaning 2, molecular meaning molecules, 2 molecules in the rate equation. That means if we increase the concentration of the base, the rate goes up. If we increase the concentration of the substrate, which is the thing that has the leaving group, then the rate goes up. So we can control the speed of the reaction with the concentration of the 2 components that we have as our starting materials. Now let's consider the structure of the substrate, which is the thing that has the leaving group. What's going to happen in your E2 reactions is, first thing, the base is going to come in and abstract a proton. The proton that it's abstracting is called a beta proton. Remember that where your leaving group is, where I've abbreviated LG as leaving group, you find that first, you back up to where the leaving group is connected. Where I put the blue dot, that's your alpha carbon. Then you look at 1 carbon away from those. That is your beta carbon, or in this case, beta carbons, because you have 3 of them. I'm going to highlight the beta carbons in yellow. So here are my 3 beta carbons. All of those beta carbons have protons on them. I've only drawn 1 to make sure it doesn't get too muddy and disorganized in here. So here's my 1 beta proton that I drew. What will happen is your base is going to come in and pull off that beta proton. You need a strong base to make this happen. And the base will pull off that beta proton. These electrons swing around, they create a pi bond, and that forces your leaving group out. Now remember, for SN1 and SN2, when we looked at those reactions, your SN2 could only happen if you had an unhindered substrate. The E2 is different because you just need a beta proton. It doesn't matter how hindered or unhindered your substrate is. As long as you have a beta proton and your strong base, your E2 reaction is going to happen. That took me forever to figure out when I was a student. I actually don't know if I ever figured it out as a student, to tell you the truth. I think I was a teacher when I figured it out. So here's the thing. SN1 needs hindered. We're going to see E1 needs hindered. SN2 needs unhindered. And you would think to follow the pattern with E2, but you don't. E2 will react with anything. It's not picky, as long as there's a beta proton. So it doesn't matter if we're looking at primary, secondary, tertiary, all of them will react. Let's consider regiochemistry. When we consider regiochemistry, let's start by looking at what the word regiochemistry means. When you see regio, think region. Right? So the region or the area of the molecule that is reacting. Let's find our beta protons again in this molecule. I'm going to find my leaving group first. I'm going to back up and find my alpha carbon. So I just put a blue dot on my alpha carbon. Now I'm going to highlight all my beta carbons. So I have a beta carbon here, a beta carbon here, and a beta carbon here. What I want you to be able to recognize is the two beta carbons that are methyls are essentially the same. They're going to give rise to the same product because they're the same group. Whereas the beta carbon that is part of an ethyl group is going to give rise to a different product. So now we have the possibility of multiple products at the end, which didn't really happen very much in substitution, right? The best you could get was a pair of enantiomers. Now we're going to have more things to choose from. What happens in our E2 reactions is when you have two different beta protons to choose from, we will see that the more substituted alkene ends up being our major final product. This has a rule, right? It's called Zaitsev's rule. When we say the more highly substituted alkene will predominate, let me show you what I mean. If you draw in the protons here, so I'm going to put a proton here, and I'm going to take my pair of electrons from my base of hydroxide. I'm going to pull off that proton. When I pull off that proton, the electrons between the proton and the beta carbon are going to come around and form a double bond. They're always forming a double bond between the alpha and the beta carbon, right? That's a thing that happens. That never changes, right? Between the alpha carbon and the beta carbon is where you're going to get the double bond. This is going to force your leaving group to leave. Now I have this structure that I'm just redrawing, and I'm going to add in my pi bond that I just created. So that would be one of my potential products. If we pulled off a different beta proton, so let's go ahead, I'm going to erase this. We're going to try to pull off the other beta proton. Let's look at this beta proton. So I have a beta proton. If I would have put the beta proton that I'm pulling off on the other methyl, I still would have gotten the same product. And I pull off this proton. The electrons will come around and they'll form a pi bond between the alpha and the beta carbons, and the leaving group will leave. So my other product is going to be this. Now I said a couple of times that if we pulled off a beta proton where I just highlighted in blue, that we would get the same product. Let's just do that really quick. Right? If we ended up pulling off that proton, I'm just going to kind of do this in my head over here. And I just redraw that structure, and I draw in a pi bond between the beta proton or the beta carbon and the alpha carbon. I would get this. And what I want you to recognize is this compound and this compound are the same compound. If you're feeling uncomfortable still with the material about stereochemistry, where you tried to look at two molecules and decide, are they cis-trans isomers? Are they not isomeric? Are they enantiomers? Are they distereomers? Then name them. If they have the same name, they're the same compound. And these are the same compound. So here are my two products at the end. Let's talk regiochemistry again. The more highly substituted alkene predominates. What that means is the alkene that has the most alkyl groups attached to the sp2 hybridized carbons is going to be your major product. That means that now, this point, we're going to start labeling things as major and minor products. So this will be major, and this will be minor. Let's talk about the more highly substituted alkene and what that means. I want to highlight the carbons that are sp2 hybridized. So I highlighted them in blue here, and I'm highlighting them in blue on my minor product as well. Let's take our attention back to the product that I labeled as major. What I want to do is count how many carbon groups are attached to my two blue carbons. I have 1, 2, 3 carbon groups attached to my two blue carbons. So we call this a tri-substituted alkene because there are 3 carbon groups attached. For my minor product, I look at the carbon groups that are attached to my two blue carbons, and I have 1, 2 carbon groups attached. So this is a di-substituted alkene. When we talk about the more highly substituted alkene, the more carbon groups that are attached to those sp2 hybridized carbons, the more stable that compound is, and that's why it is your predominant compound at the end. It's why it's your major product. So this is regiochemistry, where we're looking at the region of the molecule that a pi bond is forming, and this reaction is something that we call regioselective. Regioselective means there are more than one option for your product. All of them can form, but we're going to get more of one than another. Whereas if you saw regiospecific would mean you only get this one compound. But in selective reactions, you get a lot of different options. It's just one of them ends up being your major product. So let's look at the Zaitsev's rule one more time. The more highly substituted alkenes are more stable, and thus they predominate. Just going to get rid of that extra word there. Okay, let's look at the next page. So there's Zaitsev's rule, and then there's when Zaitsev's rule doesn't work. So sorry about that. Zaitsev's rule is a good, strong guideline. And that guideline is followed when you have a base that is small in size. If you have a base that has a lot of carbon groups around it, we call that a bulky base. And bulky bases do not follow Zaitsev's rule. They will create the less substituted alkene. The less substituted alkene is called the Hofmann product, right? So the more substituted alkene is called the Zaitsev product. The less substituted alkene is called the Hofmann product. If your base is bulky, instead of pulling off this proton, then what will happen, if your base is bulky, instead of pulling off this proton that I've drawn in green, your base will pull off one of the protons on either of the methyl groups more readily. Let's talk about why. When we're looking at this, I always imagine an apple tree. And I know that sounds really weird, but let me go through my analogy. So here's my apple tree. Not the best drawer in the world. It's going to look like a 5-year-old's apple tree. Those are my branches. And here are my apples. And I'm going to draw one apple over here. It's all the way on the outside. Now imagine that you are an adult and you are going apple picking. When you are an adult and you are apple picking, you are big and you are bulky, right? Because you're the big bulky base in this analogy. You are going to pick the apples that are easiest for you to get to, which are the apples that are on the outside of the tree. You're going to pick this apple because you can just reach your arm up, pick the apple, and it's easy. If you are a kid and you're small and you're sneaky, and you can get your little body and contort it in all different ways, and you can climb the apple tree, then you're going to be able to sneak in and get those harder to reach apples, the ones that are surrounded by more branches. So in our analogy, the easier to pull off protons are the ones that are on, in this example, the methyl group. Whereas the harder to reach protons, which are the apples that are on the inside of your apple tree surrounded by branches and foliage, are like this one. Now, it might not look like a big deal to you because you're looking at it going, what do you mean? Those are both easy to pull off. But what's happening is you have an area where not just a carbon here, you've got hydrogens all around. All right, and that takes up space. And then you've got a carbon here, and there's another hydrogen attached, and a carbon here, and more hydrogens attached, and a carbon here, and more hydrogens attached. And then once you start drawing it in Lewis structure instead of skeletal notation, you can start to see, you know what? That hydrogen that she highlighted in blue, that does have some stuff around it, right? There's some branches that are preventing me, the adult, from easily sneaking that hydrogen away. Whereas if you have a hydrogen that's on the exterior of the molecule, it's easier to remove. And that's what's going to happen. If you have a bulky base, it's going to remove those easier to pull off protons. The ones that are on beta carbons that are external to the molecule that don't have branches on them, right? So you're looking at beta carbons that are methyls. You're still going to end up getting the more substituted product. You're just going to have less of a percentage of it. So for your final products here, you're going to get the same products that we got on the prior page. The difference is going to be which one is major and which one is minor. When we pull off the yellow proton, we're going to get this less substituted alkene, which is going to be the major product in this case because this base right here is a bulky base. This is called tert butoxide. And then we're going to get our more substituted alkene as our minor product. Remember that major products, remember that the less substituted product is called the Hofmann product. The more substituted product is called the Zaitsev product. Let's just pause really quick and talk about tert butoxide. Tert butoxide is one of your most common strong bulky bases. Tert butoxide looks like this. The more carbon that you have over here where I highlighted in yellow, the bulkier the base is. Here's the problem. There's a whole bunch of ways to write out tert butoxide. You're going to see what I wrote here, the T-BuO-. You could see it with the potassium counter ion. So somebody could also include a potassium counter ion. They could write out the structure like I did below, or they could write out the word tert and then BuO-. The problem is teachers use all of those interchangeably because we forget that as a new student, you don't know that one is the same as the other. So you're just going to have to make sure that you know which versions of tert butoxide your teacher likes the most. If you are my student, I like this one the most. Let's finish up by talking about stereochemistry. When we talk about stereochemistry, what we mean is how the atoms are arranged in space. So we're not talking about where the pi bond is. That was regiochemistry. Once the pi bond has been set in a certain location, where are the groups around the pi bond? Are we looking at a trans alkene or are we looking at a cis alkene? Or if your alkene is more advanced, you would use, E and Z instead of cis and trans. When we consider stereochemistry, what we need to do is look at the quantity of beta protons. If you have more than one beta proton, then you can have both cis and trans alkenes. I want to bring your attention here toward the beta carbon that's on the right-hand side of this molecule. There's actually 2 beta protons there, which means that when we end up drawing products, our base is going to pull off this proton, the electrons are going to swing around, your bromine is going to get expelled. The simple thing to do is just to draw this product. The problem is that you can also form the cis product. So you need to also be drawing this product. The next problem is that you can also pull off a different proton. So you can pull off this proton over here, and if you pulled off the proton on the left-hand side of the molecule, what you would end up with would be different regiochemistry. These 2 are stereoisomers. This one is trans, and this one is cis. You're going to end up with both isomers, where the trans alkene is going to be your major product. Then your cis alkene is going to be a minor product. And the final, the regiochemistry one over here, is going to be minor as well. Sometimes students ask me at this point if they need to start getting a little overzealous with their majors and minors. So trans is your first major, and then cis, you're going to have more of that than you would this mono-substituted alkene at the end. But in actuality, let's not get too crazy. Let's just call them majors and minors and not rank the minors, because that sounds like a lot of work. There's one other idea that we need to spend some time talking about, and we're actually going to have a whole nother video on just this idea and the previous slide. I just want to do a quick introduction to it. If you have a beta carbon that has only one beta proton on it, then you need to do some extra work. This is going to give rise to a stereospecific product. Stereospecific means that you only have one possible product at the end. That specific is what it means. Stereo means a certain stereochemistry. So you're only going to have one potential product at the end. And what we need to do is work on figuring out, how do we know which product we're going to get? Again, we're going to have another video on this, so it's going to feel like I go too quickly. But the goal here is to have your leaving group and your beta proton be opposite one another, right? So that's anti, so anti is opposite, and in the same plane or darn close to the same plane. When we say in the same plane, do you see how I've drawn these bonds all in the plane of the page? That means that these bonds are in the plane of the page. They're all in the same plane. When a base comes in, what the base is going to do is it's going to pull off this proton. These electrons are going to form a pi bond, and it's going to expel your leaving group. And the location that these groups are in decides whether or not you're going to get the E or Z product at the end. This requirement is called antiperiplanar. You might see some people call it anticoplanar, and that's fine. The anti means that the bromine and the beta proton, and then the bromine needs to be the leaving group. It doesn't always have to be a bromine. Right, so that the leaving group and the beta proton need to be opposite one another. Periplanar means almost in the same plane, whereas coplanar means in the same plane. If they're darn close to being in the same plane, the reaction is going to happen. And that's what periplanar means. But if your teacher uses coplanar, or if you see a resource that uses coplanar, that's perfectly fine. The goal is to have these atoms in the same plane and opposite one another. Let's wrap up. In this video, we had talked more specifically about the E2 reaction. We said it was concerted and bimolecular. We said that there weren't any steric issues that we needed to consider, so a primary, secondary, or tertiary substrate will react. We talked about regiochemistry and we talked about stereochemistry. We're going to talk more about the stereochemistry requirements in another video. Thanks so much for watching. This is Katoni signing out.